Now that you've seen an overview of the design of TimedMemoizerEx, it's time to step through the implementation and see how we can use other features in the scheduled executor service for Java in order to be able to do the periodic timeouts. So this particular approach is going to use the scheduled executor service periodic timer mechanism in a space-efficient manner. The class interface is quite similar to what we had before, except this time it's called TimedMemoizerEx instead of TimedMemoizer. Once again, it implements function. Once again, it has a nested class called refCountedValue, which records the number of times a key is referenced within a given timeout period. And a lot of this looks very similar. The main difference between the refCountedValue for TimedMemoizerEx and the refCountedValue for TimedMemoizer is that the one for TimedMemoizerEx, this one, omits the schedule method. And you'll see why that does that in a second. But otherwise, it's got a ref count field that's an atomic long. It's incremented atomically every time a key is accessed, keeps track of the value. It's got a constructor that initializes these fields from parameters that are passed to it. It has a get method that's going to increment the ref count atomically and return the value. That's all exactly like what we did before. It's got an equals method, which is used to determine if a key has been accessed within the timeout period. And this will be used by the concurrent hash map remove method, as we'll see shortly. But there's no schedule method. And that's because we only schedule we only schedule something one time as opposed to once for every key value pair. So it's much more economical in its use of memory. Like before, we have a concurrent hash map that maps a key to a refCountedValue object. That's pretty much identical. And we'll take a look at how that's used in a second. We have a field like we did before to keep track of the amount of time required between purge checks. We have the function that produces a value based on a key. We have a scheduled executor service. Everything's still the same. We have a field called non-accessed value that's set with a ref count value of 1 and is used to check to see if the key has been accessed within the timeout period. That's the same. And now at long last, we have a few differences. So you can see here we have a field called cache count or cache count, and that's of type threshold crosser. And I'll talk about what a threshold crosser is in a second. A threshold crosser is used to keep track of the number of entries in the cache. And it does this because of some interesting quirks of concurrent hash map and the way that locking works for concurrent hash map. This object, this cache count object, ensures that the purge entries runnable is properly scheduled and canceled when we go from 0 key value pairs to 1 and from 1 key value pair to 0. And I'll explain why that's important later. That's the threshold that's being dealt with here. And then another field we have here is called scheduled_future. That's used to cancel the purge entries task when there's no more entries in the concurrent hash map. And of course, it's also used, it's initialized when there is an entry that's put in there. So when the threshold is crossed, then this scheduled future is created or destroyed. And then finally, we have a field called purge entries. Purge entries is the one and only runnable that is called back, and it's called back periodically, and it's used to purge the stale entries in the map. And apply will schedule this runnable whenever the first entry is added to the cache. And we'll see there's some really subtle and cool logic that makes that happen. So here's what happens. Whenever the purge entries, purge entries runnables run hook method is called back. And that's what we're defining here. We're defining the runnable itself. This is what's going to happen. The code, as you can see here, will iterate through all the entries in the map, purging entries that are considered stale. And you probably have at least some intuition about what a stale entry is. A stale entry is an entry that hasn't been accessed during the timeout period. So here's what it looks like. for each key value pair in the map, that's what the for each method does. We're going to go ahead and get the current ref count of that value. We call that old count. Then we try to remove an entry. We see whether or not its ref count is equal to 1. If it's equal to 1, it hasn't been accessed, so we get rid of it. And if it turns out that we were successful in removing an item from the map, we're then going to atomically check to see if the number of entries in the map dropped from 1 to 0. And if it did drop from 1 to 0, that means there's no more entries in the map at this point. So we're going to go ahead and cancel this periodic purge runnable, because we don't want to keep trying to purge entries from the map if there's no entries in the map. That would make no sense. It would just be wasting time. So this decrement and call it n method, we'll look at this in a second, and we'll see that that's used to check whether a threshold has been crossed, going from 1 to 0. In other words, from an entry in the map to no entries in the map, in which case we're going to stop doing this purging. Otherwise, if we didn't get rid of an item, then what we're going to do is reset the ref count for the item that we didn't purge to either be 1 or to be the current count if something has changed between the point where we took a snapshot of the ref count and here. So that's how we did that logic. That logic is the same as what we've done for TimedMemoizer. Okay, now here's the apply method. And the apply method is kind of cool. It's quite different from the one we had before. And what it does is, of course, the big picture view of this is it wants to return the value that's associated with the key in the cache. That's what it's trying to do. And the way it does it is it uses the compute if absent method. And once again, it goes ahead and for the key that's going to be passed in, if it's already got a value, it returns it. Otherwise, it goes ahead and it runs this function. And what this function is going to do is it's going to check to see if we just crossed a threshold from 0 to 1. And if we went from 0 to 1, that means we just added the first entry into the map. And if that's the case, if we're just adding the first entry into the map, then we're going to go ahead and do some stuff. So let's take a look and see what we do. So what we do is if we're going from 0 to 1, we're going to schedule the mpurge entries runnable to run at a fixed delay. And so what that means is every period, it's going to run every period. And so what will happen here is that it'll atomically schedule mpurge entries to run periodically when the first entry is added to the cache. And what that does, as we just saw, the mpurge entries runnable, when it's run every period amount of time, every timeout in milliseconds period of time, it'll then sweep through all the elements in the map, try to find stale key value pairs and purge them from the map. And we store the result from schedule at fixed delay into the mScheduledFuture field. So it can be canceled when the number of entries in the map drops from 1 to 0, as we saw earlier. Then the last thing we do is after we've gone ahead and scheduled that purge entries runnable is we return a new ref counted value, which will go ahead and apply the function on the key to create the value. And then that'll be stored in the map in order for us to be able to ref count it and have the purge entries keep track of whether or not it's stale or not. This object is the value that's associated with the key. That's the value that goes into the map under that key. And the very last thing we do here is we go ahead and we get the value, which, as you recall, if you look back at the get implementation for ref counted value, it increments the ref count atomically by 1. Here's the constructor. This constructor is the same as the TimedMemoizer class. It stores the parameters, creates a scheduled executor service thread pool with the value of 1, just one thread, and then it sets the policies to more civilized values than they are set by default. So the last thing I'm going to talk about here is this threshold crosser class. And the threshold crosser class is a very clever class I wrote, which atomically increments and decrements an internal value and then it'll call a given action when the internal value or the internal count equals a given parameter that's passed to the methods that are called. Here's the count. This is going to be, in our case, either 0 or 1, depending on which threshold we're dealing with. And then we have a method like increment and call at n, and that says if we increment the count by 1 and it equals the parameter n, then go ahead and run the action. And we're going to do this method to schedule or reschedule the purged entries task. So if we go from 0 to 1, then we go ahead and create and schedule the purge entries task. There's another method, which is also used in our example, called decrement and call it n. And you can see here, if we decrement the count and it equals n, we run the action. And we use this to cancel the purge entries task when the count falls from 1 to 0. And you can see both increment and call it n and decrement and call it n are synchronized methods. So these calls are run atomically. These actions, the check is done atomically, and the actions are called atomically as well. Now, why the heck do we need this thing? Well, we need this thing to avoid a race condition that would otherwise occur between testing whether the cache size is 0 and starting and stopping the scheduled future. So by doing things the way I show you here, we end up with an atomic check then act operation. So you can see that this will decrement and call this action if we go from 1 to 0. That's atomic. In contrast, if we tried to use methods on the concurrent hash map directly, we would have a problem. And that's because the concurrent hash map is never locked entirely. So you can see here, if we check the cache size, if we check this number of elements in the concurrent hash map, and it's 0, then between the point where we check that and we do a cancel, there's a window here because the concurrent hash map is not locked that entire time. And these two operations actually run, between the point when you check to see if the size is 0 and you call cancel, another thread could come along and increment the number of elements in the cache, and then we'd be canceling something when there was actually something that needed to be checked for being stale. So this is a race condition because these are two separate operations that are not protected by a common lock. So that's why we need the threshold crosser in order to address that particular race condition. So that's the end of the overview of implementing TimedMemoizerEx using Java's scheduled executor service.